So, hello, I'm Fabrice Benhamouda, and I will talk about new techniques for SPHF and efficient one-round PAKE protocol. And this is a joint work with Olivier, Blazy, Céline, Chevalier, Pointcheval, and Damien, Vergnaud. So, first of all, what is a PAKE, or password-based key exchange? This is a protocol between two users, Alice and Bob, who share a common low-entropy password. And the goal of the protocol is to establish a common secret key from this common low-entropy password. So, obviously, an adversary can always try to guess the password used by an honest player, because there is only a limited number of passwords. And then the adversary, Eve, can try to run honestly the protocol with an honest user, Alice. And if Eve guessed correctly the password, she will get exactly the same key as Alice. And otherwise, she will get a different key. So this attack is called an online dictionary attack. And intuitively, what we want is that this attack is the best possible attack. In other words, no adversary should be able to test more than one password for each interaction it does with an honest user. And in addition, it should be impossible to test if a password is valid just by seeing an honest transcript. So in this talk, we focus on one-round PAKE. This means PAKEs where each user only sends one flow, and in addition, the two flows can be simultaneous. And we also focus only on standard model PAKE. This means we do not want any random oracles. So, different security models have been proposed to capture the security notion for PAKE. So the first one is a BPR model introduced by Bellare, Pointcheval, and Rogoway in 2000. We have very efficient schemes with this model. For example, the COI scheme, which only requires 5 group elements to be sent per user, and plus 1 MAC element. And this COI PAKE is, free run, but not one run. But the main problem of the BPR model is that in this model, password is chosen completely at random. This means it does not really model the real world, because in the real world, users often do typing errors when they type their password, or they can also use similar passwords for different users for different websites. So that's why in 2005, Canetti et al. Proposed a PAKE model based on the UC framework. In this model, passwords are chosen by the environment, which can roughly be seen as the adversary. In addition, UC PAKE are composable with other UC protocols, but the drawback is now that we do not have very efficient scheme. In particular, most schemes require zero-knowledge proof and complex algorithm. So let us now introduce most projective hash function. Most standard model PAKE use smooth projective hash function as a basic primitive. So to define smooth projective hash function, we first need to consider a family of NP languages, LOX. So a word C is in LOX if there exists a witness W which verify a relation R with this word C. Then a smooth projective hash function is defined by 4 algorithms. The first algorithm, HKG, generates a hashing key. And this hashing key enables to compute the hash value of any word inside or outside the language. In addition, it is possible to derive from the hashing key a projection key, which will enable us to compute the hash value of any word inside the language as soon as we know a witness for this word. Okay, it's important to note that in this talk, HP does not depend on C, contrary to the original definition, if you want, in General and Lindell paper. So, okay. So what properties SPHF should verify? The first property is correctness. It also says that the hash value of a word in the language computed by using the hashing key is the same as the hash value, computing the hash value of a word in the language using the hashing key is the same as computing the hash value of a word in the language using the projection key and a witness for this word. The second property is the smoothness. The smoothness says that if, even given the projection key HP, if a word is outside the language, it's impossible to compute its hash value, or its hash value is statistically indistinguishable from a random value. In other words, HP, the projection key, does give no information or very few information about the hash value of a word outside the language. So let us now present our two main contributions. The first main contribution is the construction of an efficient SPHF for Cramer-Shoup ciphertext. And this is a very efficient one-root PAKE in the BPR model. And then the second contribution is the introduction of a new notion called Trapdoor smooth projective hash function, or TSPHF, which is an efficient one-root PAKE in the UC model. So first, the BPR case. So let us first recall the BPR Katz-Vaikuntanathan one-round PAKE framework, introduced by Katz-Vaikuntanathan in 2011. So in this framework, Alice and Bob exactly run the same algorithm, so let us focus on Alice's case. So first, Alice encrypts a password PW under an encryption key EK in the common reference string. In other words, Alice commits to her password PW, and then she computes a hashing key and an associated projection key for the language of valid ciphertext of the password PW. And the witness for this, for such ciphertext is just the random coin used in the encryption algorithm. Intuitively, the projection key will help Alice to ensure that Bob has committed to the same password as her. So Bob does the same, and then the hash value. And then the resulting key in the protocol is just a XOR of two hash values, of the hash value of Alice's ciphertext under Bob's projection key, and the hash value of Bob's ciphertext under Alice's hashing key. So the correctness is clear, and the security intuitively comes from the fact that comes from the smoothness of the smooth projective hash function. But to prove it formally, we need that the encryption scheme is in-CCS secure. So to instantiate this framework, the challenge is to find an in-CCS encryption scheme with an associated SPHF. And this is quite difficult. So in 2011, Katz-Vaikuntanathan proposed to use the Now-Young framework with El-Gamal encryption scheme. But the problem of this framework is that this requires a simulation sans NISIC. And so the communication cost is very high. It's 70 group elements per user, even using gross-size methodology. And in addition, it requires pairings on bilinear groups. In 2012, Jutla et Roy improved this by replacing the simulation sans NISIC by a relatively soon NISIC, which is a new notion they introduced in their paper. But so this reduces the communication cost to 20 group elements per user, but they still require gross-size NISIC and so bilinear groups. And so in our work, we introduce a new SPHF for Cramer-Shoup ciphertext, Cramer-Shoup encryption scheme being one of the most efficient in-CCS encryption scheme in the standard model. So we get an efficient BPR PAKE which only requires 6 group elements per user. And since we do not rely on the Now-Young framework, we do not need any NISIC, and so we do not need any pairing, and our protocol works in the plain DDH there is no pairing, nothing like that. So, and recall that the best previous PAKE was the free-round PAKE of COI, which require 5 group elements per user plus 1 max. So we are very close to, we have a communication cost very close to the best PAKE, but we are 1 round instead of 3 rounds. So let us now quickly show how this new SPHF works. So remember that what we want is a new SPHF for Cramer-Shoup ciphertext in which the projection key does not depend on the ciphertext, because in the previous framework, the projection key has to be computed before knowing the ciphertext of the other user. But all the previously known SPHF for Cramer-Shoup ciphertext was such that the projection key depends on the psi, which is the hash value of a part of the Cramer-Shoup ciphertext. So in other words, the previously known SPHF was unsuitable for our purpose since HP depends on C. And in this article, we introduce a new SPHF in which HP does not depend on C, and this yields this efficient BPR 1 round PAKE. So let us now focus on the UC case. The main problem with UC PAKE is that we need to be able to simulate the flow of an honest player without knowing the password of this player beforehand. But then still to be able to compute the resulting key K as soon as we discover or learn the password of this honest user. The problem is that in the previous protocol, in the Katz-Vaikuntanathan framework, if we want to simulate Alice without knowing a password, we have to commit to a random password, bad password. And then if we want to compute the resulting key K, we have to compute this HA, the hash value of Alice's ciphertext under Bob's hashing key, HK prime. And since C is not a valid ciphertext of the good password PW, this hash value, and since the simulator only knows the projection key HP prime of Bob and not the actual hashing key, HA is completely random for the simulator. And K looks completely random for the simulator. So we can't have UC security without any modification of the previous protocol. And the solution on Katz-Vaikuntanathan was to add a simulation zone non-interactive proof of knowledge of HK or HK prime in each flow, such that the simulator will be able to extract HK, the simulator for Alice will be able to extract HK prime from Bob's flow, and then to compute this HA value and so the key K. But such a proof is very costly, and we remark that we do not actually need to get HK prime. We just need to have a trapdoor to prime, which enables us to compute the hash value H of any ciphertext C, given only HP, C, and this to prime. So in a way, our solution is to generalize KV solution, and then we show how to construct efficiently such trapdoor smooth projective hash function. And this yields the UC PAKE, which only requires 6 group elements in the first group G1 and 5 group elements in the second group G2 for the asymmetrical bilinear group. And this works under the S6DS assumption. So more formally, what is a trapdoor smooth projective hash function? It's similar to a smooth projective hash function, except we have this additional setup to set up the common reference string and the associated trapdoor. Then we have this algorithm T-hash, which enables us to compute the hash value of any ciphertext C, given the HP and the trapdoor to prime. And we also have a last algorithm. We just check the validity of projection key, so don't bother with it. And we first remark that the smoothness cannot be statistical anymore since HP contains enough information to compute the hash value of any word inside and outside the language. So we need to introduce a new notion of smoothness. And we also need to have another property called soundness, which says that computing the hash value using the trapdoor toe prime gives the same result as computing the hash value using the ProjHash, for example, algorithm, as soon as the projection key is valid. So now, how to construct efficient TSPHF. So for that purpose, we first introduce a generic framework for SPHF. This generic framework encompasses most SPHF construction for bilinear groups or for cyclic groups. And then we show how to automatically transform such SPHF into an efficient TSPHF. So let us very quickly show our generic framework. So in our generic framework, we use additive notation for cyclic groups, and we suppose that the language can be defined as follows: a word C is the language if theta of C, if some function theta of this word C can be seen as the linear combination of the rows of some matrix gamma. And then we can define the projection key, the hashing key as a random scalar vector, the projection key as the product of gamma and the hashing key, and the hash value as the product of theta of C and the hashing key. And we remark that if the word is in the language, it's possible to compute the hash value using the linear combination coefficients of the matrix gamma and HP. And in addition, if the word is not in the language, it's easy to see that theta of C is independent from the rows of gamma, and so HP gives no information whatsoever on the hash value H. And so H is random given only HP. And we can, to embed the trapdoor, we add a scrambled version of HK inside HP, and we lift everything into GT. So finally, let us summarize our contribution. So we first improve one-on PAKE protocol in the BPR model and in the UC model. And we introduced a generic framework for SPHF. We did efficient construction for SPHF and TSPHF, and which has various applications, such as more efficient Waters blind signature and efficient zero-knowledge proof. We haven't taken a talk in this talk, sorry. So thank you for your attention.